In today's tutorial for MIDAS Civil, I will show you how to perform a nonlinear time history analysis using seismic isolators. So the first thing I will do is to close this project and to open a new one that I will save under another name called Nonlinear LRB. Okay. Now in today's tutorial I will not create the full model. I will use directly a model which has been created before. So I will only import the model, which is a MIDAS Civil MCT file inside, and I have my bridge model. So some support material section and two loads have been already assigned. So one is the self weight and one is the element beam load, so you can view it here. And now I will show you how to assign nonlinear isolators for and after that how to perform seismic nonlinear time history analysis. So I will hide again this, and now the first thing I will have to do is to assign the properties of these nonlinear general lengths. So if you go into the PPT, so again I repeat, to download this PPT and this model you can go on midasuser.com website to download the model and the tutorial. So here are the characteristics of the nonlinear length definition I will use. One for the abutment, LRBA, and one for the pier. So there will be in all 8 general lengths in the model. Okay, now go into boundary, general length, and here you have general length properties. So we'll add a new property, and in this window I will first define the first of the general length. So enter the name LRBA. The application type is a force, and it is a lead rubber bearing isolator. The self weight will be 0, and here for the linear properties I will check dx, dy, and dz. Now I have to enter the coefficients, so it will be 479,100 and 336.1 for the two others. Now in the nonlinear properties I will create I will activate 2 of these degree of freedom. The degree of freedom in y direction, so I have to define the stiffness 1099, the yield strength 15.69, and the post yield ratio 0.08917. Okay, click on OK and do the same for DZ. Okay, now click on apply and we'll create the other one for the pier, so LRBP. So again, force, lead rubber bearing isolator, total strength, total self weight 0, and 1289000 for the effective stiffness in dx direction, 0.1, 702.1, and again for the property dy, the value here will be 2204, 33.63, and 0.0862. Same for DZ. Okay, now close this window. Next step will be to create this general link on the model. So I will inactivate the section so to see a bit better what is happening, and use the zoom to create the link. So actually we don't see it, but there's already a rigid link which has been created between the node 2 and 94. So I can show you by activating it in display options, rigid link. Okay, so you see here there's a rigid link, and now we will assign the general link between these two nodes and these two nodes. So you can see also that in the walktree, these two properties you just created are in blue. It means they are not used for the moment. So click on general link, verify that you are using LRBA for the abutment. Now click on here, two nodes, and click successfully on these. Click successively on these 4 nodes to create the general link. Now I will unzoom and zoom on this part of the pier. So we'll assign the link also here, but verify that you change to LRBP for the properties and assign it to these nodes. Do the same for the second pier, LRBP, and finally the second abutment on the right. So change the link property to for the abutment and select the nodes to create the general link. Okay, now I created 8 general link, so I will close that and verify that I have 8 general links. So here you have, it's written 8, so it means that I just created these 8 general links. Now the next step, which is very important, is the mass input. So in MIDAS Civil you have 3 types of masses which can be defined: the structure mass, the nodal mass, and the load to mass. The detailed application for each type of mass are explained in the online manual. To access to it, you just have to press F1 and you will have access to this online manual. And for the nonlinear model time history analysis with general links, the mass that should be assigned to all the nodes so you can perform the analysis. So in this example, the structural mass and the load to mass will be used. So the first thing is to convert the self-weight of the elements modeled into structural mass. To do that, go in the tab Structure, and here you have Structure Type. Here, the first one. Now here you have to check Convert self-weight into masses, and select the first option, Convert to X, Y, Z. Now click on OK. Now I will convert the beam load into load to mass using this feature. So just select beam load, okay, dead load, okay, add, and click on OK. So now you added the beam load as a structural mass. Now I will create the input for the time history analysis data. The first thing will be the time history function. Unlike linear analysis, the principle of superposition does not apply for nonlinear analysis. So in this example, we will analyze both the dead load and seismic load. So it's not correct to linearly combine the separate results in this case. So for the time history analysis, we need to consider both loads acting simultaneously. And in order to reflect the dead load in the time history analysis, the time varying static load function is used. This function basically creates a condition in which the dead load is in place at the time of performing the time history analysis for the seismic load. So I will click a ramp function and assign it to the static dead load, and the ES-centro data, which is used for the seismic load, will be created afterwards. So go in the load tab, okay, seismic load, and here you have time history functions. So add a time history function. The first one will be the ramp function. So just enter the name, ramp. It is a normal data type function. And here you can enter the value of the function. So 0, 0, 2.5, 1, 5, and 1. Okay. Click on OK to generate the function. Now I will add the seismic time function. So it is very easy because you click on the button earthquake and you have a database of earthquakes. So just select the first one, center side to 170 degree. Click on OK, apply, and we'll generate another one, which will be El Centro side 180 degree. Okay, and click on OK. Now I assign all the time history functions. Next step is to input the Eigenvalue Analysis data. So there's actually two methods for performing time history analysis in MIDAS. The model superposition method and the direct integration method. So in this example, we will use the model superposition method. And the eigenvalue analysis control data are specified before defining the time history load cases. So for the eigenvalue analysis, MIDAS will provide the eigenvectors method and the Ritz vector method. I will go into load cases, and here you have eigenvalue analysis control. So you can choose one of these methods, the eigenvector or the Ritz method. So the Ritz vectors method is strongly recommended when the nonlinear model time history analysis is performed with general links, because in this case the general link forces vector will be considered and included in the starting load vector, and also the deformation of the general links will be used to calculate the starting load vector. So in order to assign that, just click on Ritz vector, define the dead load 1, the acceleration in x direction, so as we have 8 general links, enter 8, in y direction, add. Now click on include the GL link force vectors and enter 1 in the number for each GL link force. Click on OK, and we define the eigenvalue analysis control. Now we'll add some time history load cases. So the first one will be the dead load. It's a nonlinear analysis type. Analysis method is model integration. Transient type. It will last 5 seconds. And for the number of increment, I will use 0.002. So more you have increment, more the solution will be accurate. And you can enter the number of step number increment for the output. So every 5 steps, you will have an output of the results. Now damping method is model, and for the damping ratio, it will be 99% in order to accelerate a bit the convergence. Click on OK. Now we'll add another load case. So this second load case will be the earthquake. So I will call it earthquake. It's also nonlinear analysis. model transient. The end of the time step is 50 seconds, and it will have 0.02 time increment and 5 for that. Now you have to use this option subsequent to the previous load case, which is a dead load, because when you are doing time history analysis, you have to consider the loads in a certain order, because as I was telling you, it's not linear analysis, so you have to do one after another. So model, and this time we'll use damping ratio of 0.05 and click on OK to generate the earthquake load case. Close. Now I will define the ground acceleration. So go into load seismic time history analysis data, and here you have the ground acceleration. In this case, choose earthquake. Function for the direction x is the second one, LC and T, and for the y direction H. Now click on add to create this load. Now click on close. Now I have to create my time varying static load. So here you have time varying static load. Choose dead load, and the function to assign is the ramp function I created before. Click on add and close the menu. Now it should be okay, so just run the analysis, perform analysis. Okay, now I got the solution. Go into results. So the first thing I will check is let's say the displacement contour for the earthquake all. Can activate the section and legend. Okay, so if you activate the deformed shape, it will give something like that. You can change the scale factor if you want, 0.5 for example, and you can view also the animation. Click on play, and so this is the animation of this load case, earthquake all. Now we'll check the time history graph for this model. So to check that, you have here in time history tab, time history graph results text here, and in this window we'll first have to define some functions. So the first function I will define is graph function general link deform force. So what we'll check is the shear deformation on the general link number 3 in the longitudinal direction. So add a new function. The name will be n and nonlinear 3, so shear y direction. Okay, the general link is the number 3. We'll check the force at the G node, and the component is Fy. So okay, the load is the earthquake for the load case. Now click on OK. So created one. Now again I'll create another function. This time it will be the displacement in y direction also number 3. Okay, type deformation dy earthquake. Okay, now close this window and come back in the time history graph window. The first thing will define the vertical axis. So the vertical axis will be the shear, add from the list, and here the displacement will be the horizontal axis. We can define a graph title. For the y-actual decimal point we can define 1. So it's a time history graph. Click on graph to view the time history graph. Okay, now close this graph, and next thing we'll do is to check the displacement at the top of a pier using also this time history graph. So again we'll add a new function. This time check displacement velocity acceleration, add a new function. Name will be displacement pier top, and the node number is 77. To see better can view on the model. So 77, it's here on the pier top. Now the types of the result is displacement. The component is the dx, load case earthquake, include all the mode number. Click on OK. Click on close. Again in the time history graph window, so we'll define the vertical axis as the displacement pier top, add from the list, and the horizontal axis will be time. Here you can use 1 for the y-axis decimal point. Click on graph, and you get the graph of the displacement of the pier top in function of the time. So it's all for today's tutorial. Thank you very much for watching, and don't forget to subscribe to my channel in order to follow the next tutorials of MIDAS, which will be coming very soon.